We're doing Calculus, Chapter 6, Section 3, Volumes of Revolution by Cylindrical Shells. I'm your host, Dr. D. Okay, let's get going here. Alright, now we're going to be doing volumes of revolution by a different technique because we need a different technique. And let me demonstrate that fact to you. Let's say we have the function y equals 2x squared minus x cubed, which is this curve here. And we'll rope it off with the function y equals 0. And we want to rotate this thing around the y-axis. So we've got this shape then. That's nice. Okay. No, it's not quite right. I can't let that go. This is actually more difficult than I thought it would be. That's it, I quit. That's as good as we're getting it. No, all right, just a little bit more doctoring. All right, here we are. So we're rotating this thing around the y-axis. Now, we need our discs, don't we? Well, so that means a disc is going to go from there to there. From there to there, that doesn't even work. Notice it can't go from here to here because that's all one function. So you're not going one function minus another. There are no slices you could put in here. This is similar to what happened when we were trying to do dx's or dy's when we should have been doing dx's. So we need a new technique because our discs simply won't work here. Here's the new technique. It's called cylindrical shells. Here's a shell, and it's a cylinder, but it's a hollow cylinder. Now, this cylinder has a radius from the center to the outside wall, and the wall has a thickness. And then we've got a height on the cylinder. Now, just like the discs and the washers are infinitesimally thin, the walls on your shells are infinitesimally thin. So what we have here is this volume is going to equal 2 pi r, which is the circumference of the shell, 2 pi r, times h. Now 2 pi r times h is basically the surface area of the entire shell. And when we multiply the surface area times the thickness, then we get volume. So 2 pi r h delta r. Now the delta r is always going to be either dx or dy because that's the infinitesimally small portion. And so these shells are going to start around the axis and move out. And let me show you this. It's going to be easier to see in the calculus in motion. So here's our y equals 2 square root of x. And we're going to rotate this around the y-axis. Okay, so when we rotate it around the y-axis, it's going to look like this. Okay. So we've rotated this thing around the y-axis. Now, the shells that we're talking about, this is one shell right here. Now, one single shell, so we've got 2 pi r h times delta r would be the thickness of this shell. Now, we're going to have infinitely many of these shells in the whole thing. So with infinitely many shells, it's going to look like this. See, the first shell's a tiny little shell in here, and then the next one gets bigger and bigger and bigger. So we have infinitely many shells of infinitesimally thin walls. So one person described this as if we wanted to paint this shape, and each shell is a coat of paint. So you paint the first coat in here, and then as you put coats of paint on here, it's going to get thicker and thicker and thicker, and each shell that you're painting is going to get a little bit taller and taller and taller until you get this shape. So this is cylindrical shells. Now, are we using dx or dy here? Well, what's the thickness of the shell? It's a dx measurement. That's going to be the key to this. This is going to allow us to use dx where the disk uses dy, or dy when the disk uses dx. So let's go back to our original example and check this out. All right, so we obviously cannot use the disks here. What we are going to use is shells. And here will be a shell from here to here, from here to here, and it rotates around like that. That's one shell. Now, as the shell moves out across the formation, it gets taller. And then as it moves out to here and out to here, here's another shell. And then as we move back down this way, we have another shell. So we see our shells are sweeping through this just like I showed you. All right, now, let's do the math here. So I'm just going to rewrite this down here so you can see it. So volume is going to be circumference, 2 pi r, times h. That's surface area, times thickness of each shell. Okay, so let's do this thing. All right, so my volume is going to equal 2 pi times the integral from 0 to 2 of the radius. Now, what's my radius of each one of these shells? Well, it's going to be the distance from y equals 0 to y equals whatever each shell, the radius is going to be the function. So it's going to be 2 pi r no wait, I'm sorry, okay, the radius is just going to be an x value. Okay, 2 pi times the x value, which as we sweep across here, is going to be any given x value. Each radius is an x value all the way across there. So it becomes 2 pi r. Now we need the height, 2 pi r h. What's the height? Well, now the height is the function value. It's going to be 2x squared minus x cubed minus 0, top minus bottom. So 2x squared minus x cubed. And now times the thickness of each shell, which is dx. So notice we were given our function as a function of x, and now the shells have allowed us to do the integral in terms of x. So now 2 pi r h delta r. So this is going to equal 2 pi times the integral from 0 to 2 of 2x cubed minus x to the 4th dx, and that's going to equal 2 pi times 2x to the 4th over 4, so that's going to be x to the 4th over 2 minus x to the 5th over 5 from 0 to 2. And so that gives us 2 pi times 2 to the 4th, which is 16 over 2, which is 8, minus 2 to the 5th, which is 32. And 8 is 40/5, so 40 minus 32 is 8/5. So we have 2 pi times 8/5. And that means we have 16 pi over 5 as our total volume. That's it, game over. Okay, now, let's check out we want the volume of rotation about the y-axis of y equals x and y equals x squared. Now we had a similar problem with this when we were doing the disk method, and we could do this with disks. I'm going to show you how to do it with shells. So here's my we'll go 1 from here to here. And so there's my y equals x, there's my y equals x squared, and I'm going to rotate this about the y-axis, so that gives me this shape, and we're rotating this way. Now, before when we did this, we were looking at disks that went horizontal. So we would have needed to change this into x equals y and x equals square root of y. Because we needed, with horizontal disks, we needed dy thickness. Well, now we're using shells. So our shells are going to be dx thick. See, here's one shell right here, and it's going to rotate around like this. So notice our shells now give us a dx thickness, and our functions are in y is a function of x. So that's handy. We don't have to change it. Now, like I say, this is easy to change, but the example we did first was impossible to change. And you're going to have some situations where you can't get x as a function of y, because it's just such an ugly function. So, volume equals 2 pi r h delta r, which means 2 pi times the integral from 0 to 1, from x equals 0 to x equals 1, of the radius of one of these. What is the radius? It's any given x value that we want. As we're sweeping through, the radius becomes a different x value, bigger and bigger x value, but it's always an x value. Times the height. Now, in this case, the height is the top minus the bottom. So the top is the y equals x, and the bottom is the y equals x squared. So we have 2 pi r h delta r. There it is. And like I told you before, this is really simple once you get it figured out, how to put your integral together. The integration is simple now. So 2 pi times the integral from 0 to 1 of x squared minus x cubed dx, which is going to equal 2 pi times x cubed over 3 minus x to the fourth over 4 from 0 to 1. So that equals 2 pi times 1/3 minus 1/4, which equals 2 pi times 4/12 minus 3/12 is 1/12. So that the volume equals pi over 6. That's it, game over. Uh-oh. Something has gone awry. Oh, no, we got it right. Okay. Yeah, I was just looking at the wrong problem. That's a little loud. Okay. We'll edit that out. Okay. So, now, onward and upward. Okay. This time, we want to do y equals square root of x and x equals 1 rotated about the x-axis from 0 to 1. Let's see. Yeah, okay. So let's draw that first. Rotate about the x-axis. Okay, so here's our 1 right here. And we've got y equals the square root of x. So that's going to go to here. And x equals 1 is going to go to here. And we want to rotate that about the x-axis. So that's going to give us a rotation like this. And actually, I didn't need to dot that line. Okay, there's our rotation. Now, we could do this with disks, and that actually would be easier with disks because our disks would be dx thick. But now what we want to do, just for exercise, is do this with shells. Actually, this is there's a shell. And And so notice our shell thickness is dy. That means we need to change this into a function of y. So that means instead of y equals square root of x, it's going to be x equals y squared. And that's my curve right there. And so the x equals 1 is basically just that's going to be right minus left. X equals y squared and x equals 1. So now the volume 2 pi r h delta r is equal to 2 pi times the integral from what to what? Well, remember, we have a function of y, so we have to be going from a y value to a y value. So it's going to be from y equals 0 to y equals 1. Now the radius of this is going to be a y value. As we sweep the cylinder through this thing, it's just going to give us different y values as we go up. So 2 pi, the radius is y. Now the height is going to be the distance across here, which is going to be 1 minus y squared. See, it's the right minus the left. Since we're trying to find the height of a cylinder that's horizontal, then the height is going to be the right side minus the left side. And then the thickness is delta r, which is a dy. Okay, so this equals 2 pi times integral from 0 to 1 of y minus y cubed dy, which equals 2 pi times integral, rats, blew a tire there. Okay, 2 pi times y squared over 2 minus y to the 4th over 4 from 0 to 1, which equals 2 pi times 1/2 minus 1/4, which equals 2 pi times a 4th, which is pi over 2. That's it, game over. Now, if we were to do that same thing with discs, let's do that right now. Okay, this time, we're going to clean this out. Okay. Now my discs are going to be like this. Those are my discs. So I would say volume equals pi r squared, which is the surface area of each disc, times the thickness of each disc, which is the h. So this equals the integral from 0 to 1 of, oh, I forgot the pi, well, we'll put pi on there, times r squared. Now what's r squared? It's the distance from the center to the edge, which is going to be the function, which is the square root of x. So it's square root of x squared. Okay, pi r squared h. Now h is the thickness of each disc. So notice this equals pi times integral 0 to 1 of x dx, which equals pi times integral 0 to 1 is going to be x squared over 2 from 0 to 1. And this equals 1/2, so pi over 2. So it's a happy coincidence. Okay, so you can do it with discs or washers if there was a hole in the middle, or you can do it with shells. Now notice, discs here are dx thick, shells are dy thick. Now really the choice may come down to the function that you're given. See, with this function y equals square root of x, that's easy to go x equals y squared, piece of cake. So you could go either way. But some functions, like we started with, can only go one way. Okay. Yeah. One more example, then we'll wrap it up. Okay, so we've got y equals x minus x squared and y equals 0 rotated about x equals 2. So this is going to give you an example of shells when the axis of rotation is not the x-axis or the y-axis. So we've got our parabola here, and 0 to 1. Yeah, okay. So here's what we have. Okay, so this parabola goes from 0 to 1, and we're rotating about x equals 2. Oh, and notice we have and y equals 0. So y equals 0 caps it off on the bottom. Now, rotating that about the y equals, or x equals 2, means we're going to have our reflection over here. Going to go like this. And then our rotation out. Do it in red. Okay, I'm not going to put the top, but there's our rotation. Now, notice our shells then are going to be, here's one shell from here and here. Okay, so my green is a single shell. But remember, the shell starts at 0 and goes to 1. And as it moves, it gets taller and taller and then shorter and shorter. Okay, so we're ready to calculate this volume. So volume equals 2 pi RH delta R. So that equals 2 pi times the integral from... Now, first of all, before we even begin this, do we want delta x's or delta y's? Now, first thing, you can't get delta y's, you can't get dy's here because you can't get x as a function of y anyway. But the other thing is, if you look at your shell, each shell is a dx thick. So we do want dx. So we want our function in terms of x. So now we're going the integral from 0 to 1. Now, the radius of each one of these is going to be x equals 2 minus x equals some x value. So it's going to be 2 minus some random x value, because it's going to start from x equals 0, go to x equals 1. So this is 2 minus x. So 2 pi r. Now, what's my height? Well, my height is the function x minus x squared at any point. So it's going to be x minus x squared. And then my thickness, dx. There we are. 2 pi r h delta r. Now, this is going to take a little while when it's something like this, but just remember, when I'm counting a horizontal distance, I go right minus left. When I'm counting a vertical distance, I go top minus bottom every time. All right, so now that we have this, it's going to be a piece of cake to integrate. We'll just FOIL this thing, and we get 2 pi integral 0 to 1 of, let's see, it's going to be positive x cubed, and then minus x squared minus another 2x squared. So that's going to be minus 3x squared, and then plus 2x. Okay, and so this becomes 2 pi, and we have x to the 4th over 4 minus 3x cubed over 3 plus 2x squared over 2 from 0 to 1. That 0 to 1 is really handy. Okay, so now we go 2 pi times 1/4 minus 1 plus 1, and that becomes 2 power 4 or pi over 2. That's it, game over. Okay, now I want to wrap everything up and just show you the difference between shells and discs or washers. When you have a vertical axis of rotation, that means your function is rotating around the y-axis or around some value like x equals a constant. So a vertical axis of rotation. Now, if your function is all in x's, then you're best with shells, because the shells will be dx thick. But if your function is in terms of y's, then the thickness of each disk will be dy thick, and so you should use disks or washers. Now, this assumes that you can't change from dx to dy. Like if you have a function in x and you can change it to y, then you get to take your pick. But if your function is in x and you can't change it, like that first example we did, you have to do shells. And if your function is in y's and you have a vertical axis and you can't change it out of y's, you have to do disks or washers. Now, if you've got a horizontal axis, now the disks or washers will be dx thick, and so you want your equation to be in x's to do disks and washers. But your shells will be dy thick, and so if your function is in terms of y's and you can't change it, then you want to do shells. So a lot of times when there are two possible methods of doing something, a lot of students want to just pick one or the other and get good at that one and say, I don't need the other because I have this one. Well, the thing is, if you can change your equation from x to y or y to x, then you get to take your pick. But if you can't change the equation, then you better be good at both shells and disks or washers, because you think the AP exam might give you a problem that you can't change the variable? Yes, they will. Definitely. They will definitely give you a problem that you can't change it.
That's the smartest thing I've ever heard anyone say about anything.
Okay, that's it. Have fun with these.